braving the rain. It's great that you are here. So thanks for joining us today for AstroTours. My name is Gang. I'm one of the co-directors for AstroTours. I would like to begin today's event with a land acknowledgement. This event is taking place in Toronto, which is situated on the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. The territory was at the subject of the Dish with One Spoon, Wampum Belt Covenant, an agreement between the Iroquois Confederacy and Confederacy of the Ojibwe and allied nations to simply share and care for the resources around the Great Lakes. Today, this meeting place is still home to many Indigenous people from across Turtle Island, and I'm grateful to have the opportunity to work on this land. Acknowledging the traditional territory in which we live and work is a small but important step that reminds us to learn more about Indigenous peoples in these regions, to consider the history and ongoing colonialism on this land, and to reflect how each of us can contribute to reconciliation. You can visit nativeland.ca and hoos.land to learn about the land you are on and who it belongs to. Cool. If this is your first time attending AstroTours, we run tours generally on the first Thursday of most months, except for this month, obviously. After the talk, we will be heading to the lobby and roof of the McLennan Physical Laboratories and the for a variety of activities and telescope tours. AstroTours is organized and run by grad students in the Department of Astronomy and Astrophysics at the University of Toronto, and supported by volunteers who are both undergraduate and graduate students in astro and physics. We run AstroTours to share our passion, so we would really value any feedback from our attendees. So after the event, please go to bit.ly/AstroTours to give any feedback. Also there. For upcoming events, next month is our keynote, so make sure to attend if you're able to. It will be on Thursday, August 24th, and there will be a lecture by Katie Mack, who you might know as a YouTuber. She does astro videos. So yeah, it should be a cool event next month if you're going to make it. You can also go to the Facebook page of the Lowell Institute for information for the Cosmos from Your Couch video series. Tonight's speaker will be Taylor Kutra. Taylor is a PhD student in the Department of Astronomy and Astrophysics at the University of Toronto. Her research focuses on the birthplace of planets, the protoplanetary disk, and she is generally interested in how disks can affect planets that eventually form from it. Taylor did her bachelor degree at Quest University, Canada, and activity defense in a couple of weeks, coming soon. She will continue this work as a postdoc at Lowell Observatory. Lowell Observatory. Taylor also works in various outreach and community initiatives and is a strong advocate for creating inclusive spaces within astronomy. When she isn't doing astronomy, she loves to spend her time outside with her rescue dog, Shanty. So please welcome Taylor.
Oh, battery's dead.
What happened last night?
It's just fun.
Yeah. Hello, everyone. All right. Thanks so much for coming out tonight. I feel like I should be telling you like spooky rain stories. But alas, that's not the talk I prepared, even though I did almost put a bunch in right before tonight. Anyways, so yeah, I'm really just excited to tell you about how to make a planet, and basically I just want to describe to you like the world I live in as I've been doing theoretical astrophysics for the last number of years. And so basically we're going to walk through the story of planet formation, and it's been essentially the same since about the 1800s, and it's summarized by this. It's all based around this thing called the nebular theory, which Immanuel Kant, yes, that Immanuel Kant, was a huge proponent of. And it's essentially that planets just form from the extra debris from star formation. So what happens is we start off with this general big cloud of gas, and that cloud of gas becomes massive enough that its own self-gravity makes it start to collapse. And as the cloud collapses, you know, you start to get denser and higher pressure portions of the gas, and as the pressure goes up, the temperature goes up, and you get this like really, really dense hot core until boom, you get helium or hydrogen fusion. And that's how you get your star. And then the nebular theory says basically that everything that doesn't become the star just turns into planets instead. And so that's great, and you know, it's a general idea, but it's always fun to think about like the small tweaks that you can make to these sensible ideas that kind of turn the picture on its head. So now I want you to think about rotation. So this initial cloud, it's not just sitting in space completely still, it is slightly moving, it has some net rotation. And as it collapses, what do you think happens to it? The same way that like a figure skater, when they pull their arms in, of course they start to spin faster. And so, if we watch this, right, this is exactly what we're picturing. I don't know if you've spent a day looking at figure skaters doing spins before, but I highly recommend it, it's excellent. So she pulls in her arms, and you'll see here, her skirt, it just flutters right up. So in this analogy, if the figure skater is the star, then her skirt is the protoplanetary disk. And that's where the planets form. Oh, so again, here, just a couple snapshots in case you missed it. So now we can take our nice, simple little picture and we can complicate it with one extra ingredient. We start off with a cloud of gas, looking from the above on top and sort of from the side on the bottom. And we start to make that star, but to conserve angular momentum, the star pulls its arms in and it shoots out this disk. It shoots out the skirt. And that's the protoplanetary disk. And then the story of planet formation proceeds from here. We have this disk, it's full of gas and dust, which eventually conglomerate and do amazing things, and then you get planets, right? But again, it's never as easy as it seems initially, because if we zoom into the protoplanetary disk now, and we start to think about what is there and how it behaves, we have two things that matter. We have gas, which we'll think about as just like a little parcel of gas, a little cloud. And we have these dust particles. These dust particles are like, you know, dust that you're familiar with. They're little pieces of rock or ice that are like a millimeter in size. They're tiny, they're just floating around in the gas. And if now we think about, they move around the star together, the gas and the dust, but something weird happens. The way that they move around the star kind of looks like this. And you may have missed it in there, so we'll switch a frame of reference. Now we're going to become the cloud of the parcel of gas. So we're going to think about, okay, if we are the parcel of gas, how is that dust moving relative to us now? And what happened is it moves through the gas. And again, if now you were to think about yourself in the shoes of those dust particles, what's happening? Well, you're experiencing a headwind. It's the exact same thing as when your dog sticks their head out of your car window. You know, it's less cute, obviously, because it's just dust, but...
Is that your dog?
That is not my dog. I wish my dog had the jowls to do this. Oh my goodness, the picture, this would just become a Photoshop of my dog with her head out the window. But you know, unlike this dog in the car, dust grains in a protoplanetary disk don't have fuel to maintain their speed, right? So like in a car, you burn gas and you keep going at whatever speed you want. But these little dust grains in this disk, they don't have that. They have a finite amount of energy. And when the gas sort of blows on their faces and, does all of this drag, it actually steals energy from the dust particles. And what happens is over time, they'll spiral in and they'll fall into the star. And if you don't see why that is a problem, that dust grain is supposed to build and become everything that we know. These dust grains are what are responsible for literally everything on this planet. Everything was once a tiny little dust grain floating around in the protoplanetary disk. And so it's a huge problem if all of these dust grains end up in the star. We need to save them so that instead they can, conglomerate and do this like fancy little thing that we like to talk about where they hang out and get more and more and more and become a planet. And so, many, many years ago, people found a smart way to do this. What I'm showing you now is a simulation of a planet embedded in the protoplanetary disk, because what's also in a protoplanetary disk? Probably planets. And so what you're seeing, that sort of like non-axisymmetric dot, that's a Jovian planet embedded in this gas disk. And what it's doing over time, you can clearly see, it carves out this really nice gap in the disk. There's no longer any gas there. And it creates this really, really stable, really long-term feature. And, that's handy for a number of things, one of which being that the dust, as it falls into this gap that's opened by the planet, it stops. It gets held up at the outer edge of that gap. And so instead of falling into the star, the dust can accumulate and build a planet. And again, you may already see where this is going, because I just told you that in order to make a planet, you have to first have a planet. And so this leads us to this infamous chicken and the egg problem. What comes first, the planet or the ring that you need to make the planet? And this is the fun thing about this. There's not a clear solution. There's many solutions, and there's probably some parts of them that are all right, but there's nothing that solves this in particular. And so, you could say that, our model of planet formation, this thing that we've been working on since the 1800s that's been relatively unchanged, is broken, right? Throw it out and make a new one. So this is if I'm introducing you to my world tonight, this is like my neighborhood. These are like the things that I associate with, the things that I care about. What I want to introduce to you, because I made a promise that I would do this, is like my house. Like I want to drag you kicking and screaming into like my living room. Sorry. So we're gonna go straight on into theoretical astrophysics, courtesy of something that I promise you all experience: the seasons. Because what I do is I try to make these gap features without invoking any planets. And in order to do that, I take our simple model of a disk and I just add one extra ingredient. But before we get there, does anyone know what makes the seasons? Spit it out, just yell.
Because it's from the sun.
Okay, this is perfect, because I knew you were both gonna say those answers. I've taught so many people through all of these years, these undergrads, how seasons works, and those are the two answers I always get. So we'll go through the first one, the distance from the sun. Now, everyone, lots of young people learn that, planets are not on perfectly circular orbits. They're on these ellipses, these oval orbits. And sometimes they're closer to the star and sometimes they're further away. And we all have that intuitive feeling of being around a hot stove or being around a campfire, that when you're close, you're hot, when you're far, you're warm. And therefore it makes perfect sense that this would be winter and this would be summer, right? But unfortunately, that's not what causes the seasons. The Earth's orbit is in fact very, very close to being circular. And if you work it out, the point at which the Earth is farthest from the sun is actually Toronto's summer. And the point that the Earth is closest to the sun is actually Toronto's winter. So it's the opposite of what you would expect based off of just the distance argument alone. So it is, in fact, the other thing. And to deal with this other thing, we have to, go into a fake world of geometry. And so here we have the sun and the Earth. We're going to draw a line. This is going to represent sort of the ecliptic, the plane of the solar system, if you will. All of the planets sort of lie on this line. If we're to think back to sort of our protoplanetary disk, our skirt, the middle of that skirt would be this line. Like, it's a very fundamental place to be. And we'll think about another fake line that's important, and that's the spin axis of the Earth. So as we all know, right, we have 24 hours in a day because the Earth completes one rotation every 24 hours. And the axis that it spins about is the spin axis. And that axis, the direction that it points, is slightly tilted relative to the plane of the solar system. It's not perfectly, straight up and down, it's not aligned, it's a little tilted. And so that gives us a very, very fun effect. If we think about now, light coming from the sun, landing on the surface of our planet. We're going to take this in 2 steps. First, we'll talk about this, just the top area here. So this area is quite small. The concentration of starlight or sunlight there is quite large. Another way that you could say this is if you look at sort of the angle that's formed by the incoming starlight and the surface of the Earth, it's pretty large. It's close to 90 degrees, right? That's why in the summer the sun feels like it's right above you. So all of those things mean that it's summer. So there's a high concentration of starlight. It's a high angle that makes summer. Down here now, you can see relative to the top, there's a larger area. That blue curve is a lot bigger than the orange curve. So it means it has a low concentration of sunlight. The angle that sunlight is coming in is a grazing angle. It's a shallower. It's not quite overhead. And so that's what makes it winter. Okay? Now keep this in mind, because I absolutely promise it will come back to you in like a couple of slides. Because now we're going to return to our protoplanetary disk. We're going back to the figure skater's skirt. And here we're looking at sort of the side view again. So this is more what it looks like if you were to be sort of like looking at the side of a pie, looking through a cross section of the side. And now what I've drawn here, it's a surface. And with these disks, because they're just made of gas, when we think of the air in this room, we don't really think of it having a surface. But in the same way that like Jupiter has a surface, even though it's mostly made of gas, so do these disks. The same thing happens on Jupiter. This surface that you think of when you think of Jupiter is really just the location in the gas where the light from the star can no longer penetrate freely. So light from the star comes in, goes into the gas in Jupiter's atmosphere, and then gets all messed up and can no longer stream by itself. And that's what creates the appearance of a surface. And so that's the same thing that happens in these protoplanetary disks. It creates this thing that we call an optical surface, because it's optical light that is being stopped from streaming freely into the gas. And now, what's doing the absorbent of these starlight that's coming into the disk, what's stopping those photons from streaming freely? It's actually a bunch of tiny, tiny micron-sized dust particles that act exactly like little disco balls. So they have all of these little disco balls up throughout the disk. And what happens is when light from the star comes, the little disco balls absorb the incoming starlight, and then they re-radiate it isotropically. So they absorb the light from the star, and they re-radiate it everywhere. Half of that light, as you can see, is lost to space. We'll come back to that. Half of that light is shone down into the disk. And that heats the gas and the dust that live towards the center of the disk. And now, like any hot thing, like you, me, anything that has a temperature, the hot things will continue to give off radiation. And so the disk radiates, and it finds sort of this like nice equilibrium between heating from the disco balls and cooling because it's hot. Then, of course, because we're in space, there's a couple of other things going on. There's first gravity, there's the pull from the star, horizontally in this case, but there's also like a vertical component of the gravity that matters. And more importantly, for me at least, is the fact that this is a gas. This is a fluid. So unlike the air in this room, you can model it. Like you think of air flowing over an airplane's wings. You can use those same kinds of codes to model these kinds of systems. And so that's what I do. This is my living room. This is what I spend every day thinking about. And I want to show you that this seemingly delicate and balanced system is neither of those things. Because if we start off again from our plain disk, we know it's made of gas. So what's going to happen if we add just a little hot pocket in the middle? What happens to hot gas? It's shown a note.
Expands.
It expands. So in space, it's going to expand and it's going to distort this surface that we've drawn. Okay? And so now, if we think about our disco balls, interior and exterior to our little perturbed point, or the point that we heated up, those disco balls are, they're receiving the same amount of starlight that they were before, they're living their best life. But what about this region? If we think about now, the angle of the incoming photons, does this remind you of anything? The incident angle of that starlight, that little yellow arrow, is quite low. And if you think about it, think about multiple of these photons sort of going above and below. There's going to be a very small number of them that's going to be spread over a very large area. And so the disco balls that make up this very particular part of the disk, they're experiencing their winter. Okay? And now, maybe I'll try and get someone else to. What's going to happen on this other part? It's summer. Yeah. So here again, I guess the color I tried to help. Here now, the incident angle of that starlight is really, really high. It's really close to 90 degrees, meaning that portion of the disk will be able to capture more starlight. And so, yes, these disco balls are experiencing their very best summer. And the fun thing about this part of the disk, these disco balls experiencing summer, is that, not only do they get hotter, but they re-radiate that incoming radiation in all directions, but also down towards the center of the disk. And so what happens is we started off with a small little perturbation in the middle of the disk, and what we've ended up with is another one. And so I hope that you can see in this way, this small perturbation that we started off with, it could be infinitesimal, it could be tiny. What's going to happen is this thing is going to grow into this, it's going to kink this surface. And what it's actually going to do is it's going to make what we call thermal waves. So waves of hot spots throughout the disk. And so over time, not only are these waves going to get bigger, they're going to move in, and they're not only going to move in, but they're going to make more waves. Okay? So, we're getting to the end of the theoretical part. I'll promise I'll show you some pretty pictures soon. But first, I did just want to show you, because this is exactly what I do. I'm going to show you an animation that I made out of a plot that's in one of my papers. And so what we're looking at here is along the bottom is the distance from the star, and along the y-axis, or the vertical axis, is the height of the optical surface. So this is the same surface that we've been looking at this entire time. It starts off like pretty smooth, and what's going to happen is in my code, in the background, in my little black box, I'm going to shine starlight on this disk, and that's all I'm going to do. And what happens, here we go. You can see that over time, we get these thermal peaks. The optical surface kind of looks like a little staircase that we talked about before. And alternative, like, not what we were expecting, contrary to, our previous things, this is a long-lived solution, which is also very exciting. But we can talk about that after. Now, this is another plot from my simulations. Now we're going to take a top-down view of the temperature in the middle of the disk. Okay, the middle of the disk. Remember, there's like larger dust grains there, and they're emitting, and so it's very fun to see. And over time, what this is going to do, like I said, it's going to make hot rings. The lighter parts are hotter, and the darker parts are cold. So we're going to get these like hot rings that are experiencing their summer, and these dark gaps that are experiencing their winter. And the disk is just going to stay like that. Whew. Okay. I told you there would be more pretty pictures. Thank you for coming with me down that lane. Now, I'm going to do a completely different change of pace. We're going to play my favorite game that I've ever played doing outreach in astronomy. And it's called observation, simulation, or imagination. Has anyone, put your hand up if you've played this before. Okay. Excellent. I love that there's new people, because that means you don't know all the tricks. So, what I'm going to do is I'm going to show you a picture. You're going to, with the person beside you for a couple of seconds, you're going to decide which category it falls into, and then we're going to yell them out. So, is it an observation? Is it something that someone used a telescope to look at an object, took some data, and then made a picture out of it? Is it like real observation? Is it a simulation? Is it what I do? Is it a thing that came from a computer simulation that someone does on their laptop and then makes it look like a photo? Or is it imagination? Is it an artist's conception? So like an idea of what this could look like. Okay? We ready? Here's your first image. Converse.
Extent of my artistic ability.
Okay, do we need any longer? Have you thought? Have you had enough time?
Should be universe logo. I did draw, so it's an imagination.
Okay. Are you ready? Yell them out. What do you think it was? Oh, I heard every answer. I love this. I love this. This is why I love this game. And I actually love this particular round of this game because this is indeed a simulation, and it's my simulation. So what you can do after you run all of these models is you can do this thing where you go, okay, this is my disk. Tell me what it would look like if it was a photograph. And what you're actually seeing here, remember earlier we talked about those hot dust grains in the midplane of the disk? That's exactly what you're seeing, but now you're seeing it for my little lumpy staircasey disk. The hot rings in their summer and the dark gaps experiencing their winter. Okay, who's ready for round two? All right, round two. Converse.
Imagination again, for sure. It's all fake. Universe is imagined. It's all simulation. We live in a simulation. We live in a simulation. It's all simulation. What are we? It's not a simulation of ourselves. That's crazy. That's a huge contrast.
Yeah, why didn't we do that?
Yeah, and like,
that's impressive.
why wouldn't there be a chronograph?
Yeah.
Who did that? I mean, what was the data from?
What the?
Like the central one?
Yeah.
No, yeah, like which image and
Okay, are we ready?
Yeah. Yeah.
All right. Yell it out. Yes, I got you with the first one, but I did not get you with this one. This is indeed an observation. This comes from this amazing telescope in Chile called the Atacama Large Millimeter Array. And in 2018, they decided to do a whole survey of like young stars that we thought had protoplanetary disks. And this is what they look like. They're just punctuated by all of these, what we call substructures, these gaps and rings. And they're great because, you know, we know that the dust isn't dying, but the problem still arises. What makes them the planets or other things? But the thing that I really love about these is that it does indeed strikingly, minus some, you know, core differences, look like the simulations that we were able to get. And that makes me very happy. Okay, I'm pretty sure this is the last round, but I mean, it'll be a quick round, I think. You all are smart. You all count on to my tricks. Okay, go ahead.
She should have kept it. Simulation,
J.R. Tolkien.
Is this from Philip Armitage?
Huh?
Is this from Philip Armitage? Astrophysics of planetary formation?
Oh, it might be. This might be the front cover.
I don't think it is.
It's not?
I think that's
All right.
more streaky.
Shout them out. What do you think it is? Oh, interesting. Sorry to trick you, there's no imagination. This was also a simulation. I just got lazy and didn't make it look as, you know, I didn't try. Maybe I tricked you too much. But the fun thing about this, you remember when we were talking earlier and I was telling you about how the disco balls in the disk, they absorb that light and like some of it's lost to space and that we'd come back? This is the moment to come back. Because the light, we did the same process where we took this, you know, we take a code and you say, this is what I think my disk looks like. Tell me what it would look like if I had disco balls radiating off the surface and I could see the light that's being re-radiated by those disco balls just on the surface of the disk. So these are little disco balls. And the really fun thing about that is, again, you can make this observation in real life and you see similar things. You still see these bright hot spots and you see these dark rings that we think could be winter. Now, I'm going to show you one more picture because this is my favorite picture of all of them. Here, we're looking again at the light from those little disco balls that are sitting on the surface of the disk. But this disk, instead of the other disk, the previous disk we were looking right above, we had bird's eye view. This disk is inclined, it's kind of like this, right? So you can see, you know, you don't get the concentric rings, it's got some weird geometry to it. But what I like about it is that it gives you a better 3D picture, I think, of what this surface looks like. Because, you know, if you stare at this photo for long enough, like I have, you could draw some lines that you think kind of trace this surface, or you kind of trace where it is, and I would make them look something like this, where, you know, the surface sort of goes out, and then it clearly, you know, sharpens up, and then it goes out, and sharpens up, and goes out. And if I can remind you, that is again another thing that we saw in our simulations. That is what drives this what we call instability that I've been talking about all night. So that's another fun thing. All right, to taking a huge step back now to how we got here in the first place. What comes first, planet or these weird features that are everywhere in protoplanetary disks? And now obviously I've spent a lot of time thinking about how you can make disks look fun and weird like this using just this one extra ingredient, the starlight. And clearly I have my own answer to this question, but there's a reason I wanted to start this talk by telling you about an idea that we've been developing since the 1800s. It's because, you know, not all of these features are going to be irradiated rims. Not all of them are going to be planets. This is real life. Things are complicated, and multiple things can be true at once. And, you know, in spite of all of the problems that planet formation has, this idea that we've been working on, and you can get nowhere close to talking about all of them in a single, 35-minute talk. It still works, right? Planets still form despite all of the difficulties that we have found that they have. And we know that, right? Obviously, because not only do we live on a planet, but there are 7 other planets just in our solar system. And we haven't even began to touch on why some planets look one way while other planets look a different way. And beyond our solar system, we have found literally thousands of other planets in the galaxy. What you're hearing and seeing now is a sonification of the exoplanets. These are planets orbiting stars other than the sun. The size of the circle and the pitch of the note, I'm going to turn it up a little bit, tell you something about the planet's orbit. So, I spent a lot of time doing this work, and it makes me think a lot about sort of what we as people and as scientists do with these really useful stories that contain big contradictions. Do we have to just throw them all out and start new? Or can we be kind enough with ourselves to take what works for us and leave what doesn't serve us anymore? Obviously, as a scientist, I think the second option is better because I can make a mistake and still possibly have a job. But as a person, I also think that, while it's scary and uncomfortable to make a statement and be wrong, the nuance and the insight that comes along with that, I think is just really beautiful. So thank you.
Thank you, Taylor, for the talk. We'll take some questions, and then we'll hand over to MP. But yes, go ahead. So please repeat the question.
When you were talking about the problem being how does all the dust get together and not fall into the sun? They're using dark matter for everything nowadays. That's the explanation for how all the sun, the stars form because they can't see how it would form by itself. So is it possible that there's dark matter that is somehow compressing the dust into the rings so that it doesn't fall into the sun or the star?
Yeah, that's a great question because dark matter is something that we hear about all the time, and it is everywhere, but this is an effect of dark matter that, this is how you know it's a very low-key effect. Because if dark matter was doing that in the protoplanetary disk, it would be doing that on beaches, right? Dark matter is everywhere. There's dark matter in this room with us at this moment, So if the effect of dark matter is so small, and it's only a noticeable effect when there's tons of dark matter that can only happen in these huge areas. So on these scales, there's definitely dark matter in these areas. There's dark matter all throughout the solar system, but that's not the dominant force. It's so weak that it is negligible. But great question. Yeah. Oh, sorry. The question was should have done that first. The question was, how do we know it's not dark matter that's holding these planets together and is a part of planet formation? Yeah.
On the last slide, there was very concentrated group of exoplanets. I was wondering, I don't know if that's what it was, but you're like, yeah.
Yeah,
I was wondering what that is.
this one. Oh, stop. Yeah, so, let's see, nope. You can come up and look at it again if you want later. That's the Kepler field of view. So Kepler is the spacecraft that started commission in what, 2013, 2012, something like that. And it blew up the field. What it did was it essentially stared at a small patch of the sky for a very long time and looked for the changes in stars that would indicate a planet crossing in front of it. And so, because it could only stare at a very small patch of the sky, there's tons of detections there. So it's like one of these things that, like, if you look for it, they're there. But we can't look over the whole sky for them, because there's a lot of sky. You may have also noticed in the sonification, there was like this sort of like wave-like feature, like there was a bunch of little squares, like aggregates of planets being discovered at about the same time. That's TESS, which is another transit mission that's happening right now. Yeah.
Do you, so is your hypothesis that the heat waves clear a path in the gas rings, and that's another way for those gas to create? Is that what you're saying?
Yeah, so they're heat waves, which means that they set up a specific temperature. Oh, sorry, the question was, am I saying that these heat waves are causing the gas and rings that we're seeing in the observations? There's a couple of things that were moved, because this is like hot to the second, right? So you built. The first thing is that these rings that we're making, they set up a pressure structure where dust could accumulate but not be stopped. So it would be more like a pile up on the a slowdown on the freeway, where you have like fast dust coming in, and then it piles up, so you kind of like sit for a second, and then you have a slower stream of dust falling out the other end. That might be possible. The other thing that I didn't talk about tonight, these are on sort of different scales. So the structures that we're seeing in the images are slightly larger than the ones that I'm seeing in my simulations, but that's just because these are the very first simulations, and there's a reason I'm not leaving academia quite yet. Sorry, what was that?
Do most stars have planets?
Do most stars have planets? Depending on who you ask, about 30 to 50% of stars have planets. That's a question for the statisticians. They love to argue about that. But 30 to 50% of stars have planets, and on average, there are 3 planets per system. Yeah.
You find a simple model of a disk, and you add one ingredient.
Sorry, I couldn't hear you very well.
Your definition was simple model of a disk, and you add one ingredient.
Yeah, that's how
Okay,
yeah.
what was the ingredient?
Oh, starlight.
Starlight.
Yeah.
Okay.
That's it.
Oh, yeah. Okay, I just remembered my question.
Okay.
Can you explain the sonification of planets? How does that work, what you just showed us? How do they do that?
This is my favorite video that I've ever experienced. So the guy who made this is actually, he used to be a grad student at U of T. His name's Matt Russo. He now does like sonification work for NASA, because he's also a musician. And so what this is actually, you can go online and you just look up sonification of exoplanets, and I'll tell you all about this. So the different colors are the different detection methods. The pitch of the note tells you, I think, the planet's mass. So like the smaller the planet, the higher the note, the like deeper the note, the more massive the planet. The size of the circle, I think, tells you the orbital distance of the planet. It's just like a really, really satisfying and beautiful way to conceive of like this data set that feels kind of, untouchable.
Wait, what did you say is the size of the orbit tells you?
Sorry, yes. size of the orbit. So the pitch of the note is the size of the planet. The size of the circle is the size of the orbit. I'm pretty sure, but I haven't looked it up in the net, so. Yeah.
I was just wondering whether it was your idea to include starlight in the modeling, or have others done the same thing?
So like most things, there's like this paper from 2008 where they did this kind of thing with a code that doesn't take into account the fluid movements. And so then they found these thermal waves. And then my advisor wrote another paper where she didn't take into account the fluid hydrodynamics. And they also were able to get these thermal waves. And then when I was writing my thesis, we were like, all right, what are we gonna do? And I was like, I can do hydrodynamics. And she was like, all right, let's go. You know, sort of like one of those like kismet opportunities. And it was like, let's do it.
Does the particle emission from the sun account for it, or it's very relevant fact?
The particle emission?
From the sun, like the ions of the sun.
Oh, like,
are they counted, or they will very relatively matter?
So you're talking about sort of like solar flare
Yeah.
type particles? Yeah, so we don't account for that. I don't think that they would make a huge difference because the region where this is active is largely an unionized region. So any magnetic effects are negligible. And also, I don't think there would be very much solar flares, or like flares of significance at these distances. Yeah. How much, what are we doing for time? Couple more minutes. Okay, I'll take 2 more questions. Yeah.
So, in a lot of the images you showed, there was sort of, well, not a black hole, but a black hole in the center, and I couldn't see light in the center, so isn't the star there? Why doesn't it show?
You're talking about this one? Is this one that you were thinking of?
Yeah, but then also a few others, I think.
Okay, so this one in particular, because as I'm sure we're all aware, stars are bright. That's why we can't look at the sun, right? And so if you're like looking up at the, say it's like a nice, you know, one of those like fun days where it's nice to go out and like look at the clouds and like look for shapes in them and stuff. If you want to look at a cloud that's like right next to the sun, you have to block the sun, right? Because you want to be able to see the slightly dimmer thing that's next to it. Do you know, have you all had a similar experience where you want to see a dim thing that's next to a really bright object, so you like put your finger and you're like, that's what the telescope is doing. Yeah, so it's called a coronagraph. And so that's what that little dot is they take the star and they go, and then they take a picture of what's around it. Yeah. And then at the back there.
Okay, so there's one thing you didn't address, which is what causes the speed differential between the dust and the gas in the first place? And why does the dust move faster than the gas?
It's because of pressure, really. Because the gas is a fluid, and so it experiences gravity the same way that a rock would experience gravity, but it also experiences a force of pressure. And in a rotating disk, the force of pressure actually opposes the force of gravity. So pressure wants the gas to spread out, while gravity is trying to pull it in. And the net effect of that is that what really is happening, like mathematically, is that the gas is experiencing a slightly less massive star because of the effect of pressure. Yeah. Okay, last question? One more. Yeah. Another great question. I put this on because I love this photo so much. That's the other side. So in these photos that I was showing you sort of just like the one half, and there was always another half, and it's just kind of like there, but we don't really worry about it. In these images, you can actually see the other side. So it kind of looks like a donut because this is it's hot, but it's shining through the gas. So if you can imagine in 3D, it kind of has 2 cones that go like this. Yeah. Cool.
Great, thank you so much, Peter. So I would just ask for your patience for a few more minutes, just to go over a couple of things, and then we can head over to MP to look at the telescopes. So AstroTours is run by volunteers, so thank you to all volunteers for helping making this event happen. We are also sponsored by these people, the department and yada yada. The Center for the Canadian Institute for Astrophysics and the Dundas Institute. Anyway, you can, so we will be heading to McLennan Physical Laboratories in the lobby and in the roof. The roof will have telescopes and the lobby will have demos. They will be happening until 10:30. One of our volunteers will help you bring over somewhere. Remember to fill out our feedback form here. We really appreciate any feedback, and it will really help us run our event. And here's the map to the building if you want to walk yourself. Thank you so much.
Your frustration with admin was very
Greg came in screaming into my living room, came out of my mouth, and I was like, that was appropriate.